Okay, we're back. We're going to introduce the next idea. It's a scalar product or a dot product of two vectors. Okay, a scalar product is what they call it in the book, but quite honestly, it's usually referred to as the dot product between two vectors, p and q, is defined as the following. P dot q, so it's the dot, this is a dot product, the little dot symbol, is the magnitude of p times the magnitude of q times the cosine of the angle between the two. And the reason they refer to this as a scalar product in this book is it produces a scalar. The end result is a number. It's not a vector, it's a number. It's a scalar. Okay, some properties of scalar products. They're commutative, right? Which is nice. Remember, cross products are not, but scalar products are. So p dot q is the same as q dot p. They are distributive. So p dot q1 plus q2 is p dot q1 plus p dot q2. We'll use that here in just a minute. And lastly, they are not associative. And this is one where, if you think about it, it makes a lot of sense. P dot q, it's a scalar product. So a scalar product or a dot product takes two vectors as inputs and produces a scalar. So when I take these two vectors, the output of these two vectors is going to be a scalar. Well, a scalar dotted against a vector doesn't make sense. We just defined a dot product as having two vector inputs. So you cannot, the order matters, and you cannot just continually dot them against each other. Now, let's talk about the Cartesian components of these scalar products. They're actually pretty straightforward, and it's kind of a convenient thing. Let's look at I dot I. So I dot I, we come up here. I dot I. Well, the magnitude of I is 1. The magnitude of I is also 1, because it's also I. So it's 1 times the cosine of theta. So what is the cosine of theta? Theta is the angle between the two vectors. Well, if they're pointing in the same direction, the angle is 0. The cosine of 0 is 1. So therefore, it's 1 times 1 times 1. So I dot I is equal to 1. J dot j, by the same reasoning, is equal to 1. K dot k is equal to 1. Everything else is equal to 0. Why is that? Well, because then all of a sudden your theta becomes 90 degrees and cosine of 90 is 0. And so these become 0. So if we have this vector p dot q, vector p dotted against the vector q. So you have your pxi, pyj, and so on. Well, again, we're going to distribute it out. So pxi dot qxi. So it's the magnitude of px times magnitude of qx, I dot I, which is 1. Right? So you have px and qx. And then this one times this one. Well, the magnitude px times qy, but then you have I dot j. And we just said I dot j is equal to 0. And then same thing this one and this one, but you end up with I dot k, which is also 0. So when you go through and you do the math, it works out that it's just that you just multiply the x components together and add it to the y components, and you add it to the z components, and that is your dot product. So taking the actual part of doing the dot product is actually nice and easy. You just simply take your x components multiplying against each other, the y components and the z components, and you add them all up. And if you dot a vector against itself, you end up with the square of the magnitude of that vector. Okay, why do we care? Well, a dot product can be used to find certain things. The first thing that we're going to use it to do is to find the angle between two vectors, right? So you have a vector, boom, boom. Well, we don't know what that angle is, but we know what a dot product is, right? A dot product of p dot q is pq cosine theta. Well, if we know p, we know the magnitude and the direction. We know q, the magnitude and the direction. We can figure out the dot product, because again, we just said this in the previous slide, right? It's the px qx plus py qy plus pz qz. So that is the dot product, and that's equal to the magnitude of p times the magnitude of q times cosine theta. So you can arrange this and solve for cosine theta, or you can find theta. So this is one of the primary reasons you're going to use dot products. It's to help you calculate angles between vectors. This is huge. The other primary reason that you're going to use dot products is for a projection of a vector on a given axis. Okay, and we'll do an example of this, and hopefully this will be a little more clear here in a second. But what we're talking about is you have a vector p. So how much of this vector p lies in this direction of OL, right? So we have p dot q. So what we're going to do is POL, it's p cosine theta. Everyone buys that, right? That's just like our x component over y component. So POL is p cosine theta. But p dot q is PQ cosine theta. Well, you'll notice if you divide through by Q, all of a sudden our dot product divided by the magnitude of Q gives us our P cosine theta, and that is what we already discussed. That is our projection of P along the OL axis. So you can take the dot product and divide by the magnitude of the one, and you get, boom, you get how much of that vector is along that axis. Again, we will do an example of that here just real shortly to make that more clear. And then the last part is an axis defined by a unit vector. You can dot a vector times the unit vector, and it'll tell you how much of that vector lies in that direction. Okay, the mixed triple product. So here's the deal with the mixed triple product. Mixed triple product is one of those things that I personally don't do this. It's S dot P dot cross Q. This is useful. I just do it in 2 steps. It can be done in 1 step. If you're using the book, if you look at the solutions, you will find this on occasion. And so I want to show you this, but it's not something I personally use. So the mixed triple product of 3 vectors is S dot P cross Q. Remember, you can't do this in any arbitrary order. It matters. Because P cross Q does what? P cross Q is a vector product or a cross product, and it produces a vector. And then you have S, a vector dotted against a vector, and that's going to produce a scalar. Okay, so the mixed triple product formed by S, P, and Q, they all have equal magnitudes, but they're not the same sign. You can go through and you can convince yourself of that. To evaluate the mixed triple product, this is the key, is S dot P dot Q, or P cross Q, you use a determinant. But remember before when we did the cross product, we have I, J, K. Well, instead of doing I, J, and K, we're going to go ahead and put the X, Y, Z components of what we're dotting it against. And then this is basically the cross product right here. So you have, whereas if this is pure cross product, we do I, J, K, and we'd go through and we figure out our cross product, would just have I, J, K components, and then we'd dot it against the S. So then you'd multiply the X component times the X component, Y times Y, and whatnot. Well, we can do that all in one fell swoop with a determinant. Boom, here's the S, XYZ, P, XYZ, and Q, XYZ. The order does matter. Remember, you'll get a different sign if you change this order. Again, this is useful. You're welcome to do this. It's not something I do. I will do this in 2 separate steps, and I'll show you why. Right now. If you want to find the moment of a force about a given axis, okay? So take, for example, you have a door. You're trying to close a door. So you're pushing on this door, and some of that force of the door is causing a moment to close it. Some of it's causing a moment that, say, is trying to rotate the door off the axis, which is not going to happen. You know, it's only so much of what you're doing is actually closing the door. Well, we can use a mixed triple product to determine how much of that moment that you're producing on the door is actually closing the door. Okay, so what we're going to do is we're going to find the moment m0 of a force applied at the point A. Sorry, the force is applied at the point A about the point O. Right? So you have a force, this is what you're pushing on the door, in some force in some direction. And so you figure out what is the moment about this point from this force. Well, how do we do that? Moment is R cross F. So you define R cross F. And then you say, okay, I only care about a certain portion of that moment. I only care about the portion of that moment that is in this direction, right? So this R cross F gives me this moment MO. Well, this MO has a X, Y, Z component, but it also, you can break it into how much of it is along this axis and how much of it is not, right? So how do we figure that out? Well, that's what we use a dot product for, right? We're going to dot this vector, the moment vector, which is again this R cross F, so it produces a moment vector. We're going to dot that against lambda. Why do we do that? Because that tells us how much of this moment is in this direction. So again, imagine the hinges are here, and this door needs to rotate about this axis right there. Well, no matter what moment is going in the other directions, the only portion of it that's going to actually open the door is a moment that is rotating about the hinges. And so we're going to say, okay, hey, we've produced this moment, but how much of it is actually doing what we want to do? It's the portion that lies along this axis. So it's lambda dot m0, but as we just showed, m0 is R cross F, so lambda dot R cross F. So you'll notice this is a triple product. Again, I personally, when I do this problem, So here you can write this as a triple product, lambda x, y, z, r, x, y, z, and f, x, y, z, and you can figure out your moments. I personally would just end up doing this, and I'd get some moment, and my moment would have an x, y, z component of it. I would have this moment, and then I would dot that against lambda x, y, z. I just do it in 2 steps. I just find it easier to think of it that way, but either way is fine. Now, something to note. The moment x, y, z are to moment what force x and y and z are to force. So what do I mean by that? It's just to say that the x component of the moment is the portion of the moment that makes it rotate about the x-axis. The y component is the portion that wants to rotate around the y-axis, and z the z-axis. This is actually really important to understand because a moment is a vector. And just like other, we've gotten used to this idea of these force vectors that they have the x component, y component, z component. Well, we also have these moment vectors, and these moment vectors have their various kind of jobs. And the x component, or the job of the x component of the moment vector is to rotate this thing around the x-axis, and so on. And so you can start to, just like you can look at a force vector and consider, hey, there's this much force going off in this direction. It's the same with moments. There's this much moment, this much tendency to rotate about this axis, this much to rotate about this other axis. Okay, so now this is again the same thing, but it's just what happens if our arbitrary axis doesn't pass through the origin. Well, it's the same thing. It's r cross f. It will always be r cross f. Moment's always r cross f, but now we define r from b to a. And so that's you go through and you figure out the moment, which is r cross f, and so that's the moment about point B, but then we're going to say how much of that moment is in this direction, so we're going to dot it against lambda. And when you go through, you can figure out that the result, how much of that is about this axis, is actually independent of the point B, because when you go through and you figure out, when you define your r's, that it doesn't matter. How much this rotates about this line doesn't matter whether you consider this point of this line or this point of this line or any of that. It's going to be independent of that. Okay, let's do another example. This is example 3.5.